Let's now see how we can use discrete event simulators to model customer queue worker systems. So we have systems such as these. There is a source, for example, the entrance door, where people come in. And there are plazas where people can be and decide where to go next. So, these can be inside an airport. When you enter, you need to decide which queue for the check-in to join, or if you are in the supermarket, this plaza can be the inside of the supermarket, and you have to decide for which cashier to start lining. Then there are queues, and there are workers that service the customers that are in the queues. Okay, and you can have various architectures. This is an architecture in which every worker has its own queue. So when you need to say check out of a supermarket, you need to decide which queue to join for the cashier. But you could also have other architectures. So let me actually zoom ahead and show you. For example, you can have each worker their own queue, or you can have a single queue for all the workers. Airports for the check-in often work in this way, right? There is a single check-in queue, and then you can go to talk to one of the various people at the various counters. So we want to be able to model this type of systems. So let me go back up again, and if we want to do this, we will have to have objects that are source, plaza, queue, worker, and a plaza without queues connected to it will be the exit simply. Okay, so we have various types of classes. We have a person class that will be the people traveling through this network. We have a worker class which represents the workers. We have queues. We have plazas. And we have sources, okay? And in order to understand the interaction, let's switch to a drawing. So source, plaza, queue, worker have events, and they interact with each other. And I want to explain with a drawing what their interaction is. So here is a drawing of our main classes. I haven't drawn the person class because that one has only one event, as we will see, that is triggered when the person is done with it. So the source has a start event used to generate the next person. So what does this event trigger? The start event will trigger two things. It will trigger a future start so that we can generate a never-ending stream of customers through the network. And it will also trigger the enter event of a plaza. The enter event of a plaza will trigger the enter event of a queue. So there is plazas are not equal to queues simply because you can have multiple queues getting people from the same plaza, right? So we want to keep a distinction. But whenever somebody enters a plaza, they will enter a queue next. So, this event will trigger a queue entrance next. If a person enters the queue, two things happen. Actually, one thing happens. When somebody enters the queue, there is a notification to the worker. Now, the worker may be busy, in which case the notification is lost, right? The worker receives the notify event, but just disregards it because it's serving other customers already. But if the worker was idle, the notification would be used so that the worker can actually go and fetch the person from the queue and start serving the queue. The worker, either as a response of the notify event if it was idle, or in response to a previous finish event due to finishing serving a customer, has this finish event. The finish event is used to represent the fact that the worker is done serving a person, okay? The finish event may trigger another finish event in the future because, the worker may actually fetch a person from the queue and get it. Or if there is nobody in the queue, then the worker simply becomes idle. So this is a very simple picture of how events trigger each other across these objects, okay? And now I want to show you how this is actually done in the code. So this is a code for a person. A person has a finish method that triggered when the person is done for the network, and all it does is records the end time so that we can compute the elapsed time. Nothing very interesting. A source is also quite easy. It has a start method, okay, and this start method will generate two events. You see, it generates a start event and an enter event. The start event is defined here, is an event of self-start with a delay that is equal to delta t. So this is the process by which the start will trigger itself again, as we have seen in the previous examples of the bus stop and the bus, right? So this produces the infinite sequence of starts, and so the infinite sequence of people. This delay delta t is sampled according to a gamma distribution that has a certain rate. Okay. The enter event is also triggered, and is the event of the person that is generated entering the plaza. And so this is an event that causes self.plaza.enter. Self.plaza is the plaza associated with the source. Every source has to have a plaza where it puts the people created. So this will call the enter method of that plaza with as an argument which is the person that has been created. Okay? So the source essentially has the purpose of putting people in the plaza. So it generates a person, and it returns two events: the person entering the plaza and the start of the next person. Okay? Now, what does a plaza do? Well, the plaza simply generates an enter event for a queue. So you see, it returns only one event, which is queue.enter with arguments of the person. And so all this code here, all this yada yada, is just to say, well, how does a person choose the queue? We could model different plazas. We could have a blind plaza in which people choose a queue at random, or we could have all kind of crazy stuff. But what I implemented here is a very simple plaza in which people actually look at the queues and choose the shortest one, which seems somewhat reasonable, right? So the way I implemented is this. The plaza has a method register queue, because I have to be able to, assemble this network of queues, plazas, and whatever else. So when I have a queue, I can register it to the plaza, and is put in self queues, and then I simply check. What is the length of the various queues, and I will append the person to that. Okay. I also keep track of everybody who has visited a certain plaza. This is useful, especially to be able to do graphics at the end. I want to know, hey, everybody that went through this particular place, how long did they take to do this and that, right? So this is simply done for visualization purposes, but I keep track of the visitors to a plaza. And then I look at the shortest queue and add the person to the shortest queue. Okay, I do random choice in case, just to break ties. So this is how a plaza works. Now, let's look at how a queue works. A queue has a list of people, and it has this, this method register worker, so that you can attach one or more workers to the same queue. A queue can have multiple workers to service its customers, like in an airport setup where there is a single check-in queue and then there are multiple workers that get people from it. And so it has one event method, enter. So when a person enters the queue, I append it to the list of people in queue, right? And then I say, for every worker that is getting people out of this queue, I notify them that there is somebody in the queue, so that if by any chance any of these workers was idle, they could start serving the new person. And I return these new events that are all notification events as the result. Okay? Then this method exit is simply used by the workers to pick the right person. Okay, and then it has a length, and it has a property that says when it's empty. So it's quite simple. Let's look at a worker. A worker has the following: a queue from which to accept people, a plaza where to send people once they're done, a delay factor, which is how fast the worker is, and a busy flag, to remember whether the worker is busy servicing somebody or is free to accept customers. There is an internal method, getPersonFromQueue, that essentially checks the queue, and if the queue is empty, it returns no event because there is nothing that needs to be scheduled in the future. And if the queue contains somebody, it picks this person from the queue and it generates the finish event for that person. So with these comments, let's look at the actual code. When you create a worker, you specify a queue, okay? The worker can serve only one queue. And when you specify the queue, the worker registers itself to the queue, okay? So this sort of notifies there is this two-way connection. You specify also a plaza. Busy initially is false, right? And the delay factor is how fast the worker is. So get person from a queue does the following. It takes a person from the queue. If the person is none, because this could be the case actually. So if the person is none, it returns the empty list. No events in the future are needed. Otherwise, it turns itself busy. It chooses a delay for when the person will be done with the worker, and it generates the event finish with that delay for that person. Okay. So if the worker gets a notification from the queue, it either ignores it if it's busy, or else it calls self get person from queue to exactly start servicing that person. So if the worker is idle, there is no future event for that worker in the timeline. When it gets that notification, the worker picks up the person from the queue, starts servicing the person, and so returns this finish event for the future. When the worker finishes with a person, what does it do? It generates the event in which the person enters the plaza after the worker, of course. And then it does the following. It sets itself to false, because busy to false, because of for the moment it is done with a person, and then checks, is there somebody in the queue? If so, it starts servicing the next person, and it returns the new events. So it's all actually quite simple and logical if you think about it. Now let us use our code in order to model some queue scenarios, okay? So this is a source of people, there is a plaza, and then there are multiple, imagine supermarket checkout workers, each one with a queue in front of them, okay? So you have to decide for which worker to line up when you are in the supermarket. And we created these things with a twist. So if you look at how I create people, okay, there will be some people that are much slower than others. Okay, some people will have a lot more products in their cart, essentially. Look at the code for source to understand it. So some people will be slower, and also the workers don't have all the same speed. There is a W1 which has a delay factor of 2, W2 of 3, W3 of 4, indicating that these workers have different efficiencies. W1 is fast, medium, and W3 is slowest. Okay, and these people don't know where they are in the plaza. They just join the shortest queue. So this is our first system. We can simulate it. And so look at how I create it. I created the entrance, the way out. The entrance will be the source, right? These two are plazas. These are the two plazas. I created the entrance and the way out. I created the source. Then I created the 3 queues, and I created the 3 workers. And then I need to connect them together, okay? I attach to the entrance the queue Q1, Q2, and Q3, okay? I need to do these connections. Then I say that I created the event for the source to start, okay, and I add it to the event simulator, okay, and then you know, it's just enough to start the source, so this will start creating people and everything else runs on that. And then I simulate for a certain number of steps. So I define here the parameters, okay. The number of steps is gonna be 200,000. The source number, we're gonna create 10,000 people to go through it, etc., etc. So those are the data for what we are gonna simulate. So if I run this simulation, let me run it. Wait, did I run it? Okay, so if I run the simulation, what I can then display, look at this histogram time implementation, but is the histogram of time people take and how long they take for 95% of the customers to be done. So 95% of the customers, you know, or most of them, if we take that as the most assumption, take 34 time units to be done through the system, okay, with this type of network. And so let us use exactly the same source parameters and number of incoming people and speed of the workers, etc., etc. That is why I define them once and for all here. Let us use exactly the same parameters, but change the arrangement of the queues and specifically adopt a single queue in front of the workers, okay? So now I use this implementation. So I create a different network, but the source has the same parameters and the simulation is run in the same way. So if I run these, let me run it. Okay, so this is a time distribution I obtain, and the 95% time now is 20. So before, as you can see, it was 34 point something. So it's markedly more efficient in this case to have only one queue. Okay, why is it so much more efficient? Because if there is only one queue, customers don't have to try to guess which queue to join. You know, normally when you're in a supermarket, you always do this eyeing, you know, you want to know which cashiers are faster. And especially you don't want to line up behind people who have a huge amount of stuff in their cart, right? Because that will take longer. And so there is a lot of guesswork. And here in this model, people just join the shortest queue. So they are oblivious both to worker speed and to how big the carts are of the people in front. In this model, right? So this model will take longer to complete. You will need a longer time for 95% of customers to have completed, because there is a larger percentage of unlucky customers that end up, you know, behind bigger carts and slower workers. Whereas here, you know, there is a single queue, and so everybody has a more average experience, and there are fewer unlucky people. And so that's why this 95% time completion time is lower. And we can also have fun in building two-stage networks. So imagine that you enter some place and you have to go first through, I don't know, the check-in worker and then through security. Okay, so there is a way in which once you decide lane 1, lane 2, or lane 3, you are stuck in that lane. And there is, of course, I tell you right now, another way in which there is a single queue, then there are multiple check-in workers that pick people from the same queue, and then there are, you know, there is a single security lane, and there are multiple screeners that take people from the same queue. And so we can build these simulations and run them, okay? So we can run these simulations. Okay, and if people have to choose the lane and then they are stuck in the same lane, that is in this architecture, the 95% completion time is 86 and something, almost 87. And instead, if there is a single queue from which the workers pick up people, we can run it again, and we see that it's only 55. So also in this case, there is a market benefit to have shared queues. Okay? And so this is really not too complex an example, but I think it's it's a very nice simple example of how to build an event-driven simulator that actually simulates a reasonably meaningful physical system out of which you can draw results. If you want to simulate rod networks or more complicated systems, well, now you have the means. You just have to build, a more sophisticated model in each of the objects to reflect the behavior.